Alright, so we're going to talk a little bit about orthogonality and orthonormality. Now before we delve into the definition of the actual words, let's get ourselves some tools to work with. So let's define a set of vectors. Let's call this set of vectors S. And let's put in some nice pretty vectors in here. So V1, V2, and let's go all the way up to Vk, where k is some arbitrary number. Now, we can say that S, the set, is orthogonal if every pair of vectors in S is orthogonal. So what does that exactly mean? So for all, and once again, an upside down A kind of thing is the symbol for the words for all. So let's set for all I and j, such that I is not equal to j, we say that Vi is perpendicular to Vj. And that is true if and only if Vi dotted with Vj is equal to 0. Add 0 to the scalar because a dot product returns a real number. So we call this pairwise orthogonality, where every pair of vectors in a specific set is orthogonal, where their dot product is 0, or their inner product is 0. So this takes us into an interesting theorem, which is that every orthogonal set of vectors is also linearly independent. Now, what exactly does that mean, and how can we prove that? So the theorem states that, let's again use our set S, if S is orthogonal, so which means that it satisfies this expression, and Vi is not equal to 0, the vector for all I is in this. So as long as S does not contain any 0 vectors, we say that S is linearly independent. Now, for a quick proof, of the theorem, let's get an arbitrary j that is in. We take a value of j that is within 1 and k, so it is within the set of S, and we dot this vector Vj with A1 V1 plus A2 V2 plus all the way to A2 Vk. Now our goal is to show that A1 and all the values of A are equal to 0, and we don't want to show that that is the only solution. So let's assume that this should be a k, not an epsilon. Now let's operate under the assumption that A1 V1 plus A2 V2 plus plus AK Vk is equal to 0. We don't know exactly what the coefficients are yet, but let's just say that this equation holds true for some coefficients. And we want to show that all the coefficients are 0, and that is the only way to satisfy this equation. So again, we set this equal to 0, and again, I can distribute this set. So we know that A1 V1 dotted with Vj plus A2 V2 dotted with Vj plus plus AK Vk dotted with Vj equals 0. And we know that S is orthogonal, which means that all of these expressions are going to go down to 0 with the exception of one of the expressions. So all of these eventually drop out with the exception of Vj dotted with itself. Because Vj is in the set, so therefore at some point it becomes dotted with itself. So we know that A Vj dotted with Vj is equal to 0. Now, because the 0 vector is not in S by our assumption here, because Vi for all values of I1 through k is not equal to 0, we know that Vj is greater than 0. therefore, the only other way this could be satisfied is if a equals 0. Because the only way for Vj dotted with itself to be 0 is for Vj to be 0. So we know that. So therefore, a is equal to 0 for all j is in 1 to k inclusive. So again, because S is orthogonal, means that all of these drop out, which leaves us with only one set, and that's A times Vj dotted with itself, and Vj cannot be 0 because we already stated that there are no 0 vectors in S. And because, like I said, because S is orthogonal, these drop out. Therefore, the only way for this to be true is for A to be 0. And that holds true for all values of j because you can just iterate through the entire set. So that leaves that theorem. So now we have a concept of orthogonality in sets. So let's talk about orthonormality. And again, I'm just going to leave our little set S on the board. So let's say that a vector v is called normal if its length, and we denote length of vectors by double bars, is equal to 1. And just by the etymology of the word, we can see that a set of vectors, let's call this set vector, let's have them have the same names, but let's just put a different name. Same vectors, but just let's call it t. This set of vectors t is orthonormal if it is an orthogonal set of vectors with length 1, also known as unit vectors. So an example of this is the set of the standard basis vectors. So we have epsilon 1, epsilon 2, all the way down to epsilon n for any n by n matrix. So this is an example of an orthonormal set. There are a variety of other orthonormal sets, and we will actually find a way to calculate orthonormal and orthogonal sets in the next video. And again, this leads us into an interesting theorem where we can find the coefficients of a linear combination. So let's erase this definition here. So let's have a theorem if T is a basis in any inner product space. And let's refer to this product space as V. And if an arbitrary vector y is in V, such that y is equal to a linear combination of the vectors of the basis, because it is a basis, then two statements hold true. If T is orthogonal, then any coefficient of this linear combination equation is equal to y dotted with vi over vi dotted with itself. Or 2, if T is orthonormal, then AI becomes a much simpler equation, and that's just y dotted with vi, because this drops out as the length of 1. So let's prove that. And I might not have room on this whiteboard. So again, we have our value of y, and now you can write that down to save space. This is our value of y. Now we can dot y with any number, any vector vi. It's referred to as the vector somewhere in this set vi. We can dot that, and by the previous example, by the previous proof, we can also distribute it. So we have a v1 dotted with vi, and plus a v2 2 dotted with vi plus a v, we said that it is going to go up to k a v k dotted with vi. So again, we have this equation, and we know that one of two things holds true. Either t is orthogonal or t is orthonormal. So let's work with t being orthogonal first. Since t is orthogonal, which means that all of these pairs of vectors are also orthogonal, again, with the exception of vi dotted with itself. So this drops out, all of this drops out. So we have 0 plus, I'm just going to simplify that even further, a vi dotted with vi. And so y dot vi is equal to vi dot vi. And now we can just, since this is a real number, we can just divide both sides. So y dotted with vi over vi dotted with vi is equal to a. And it is very easy to see how if t is orthonormal, this just becomes 1. So that is a brief definition of orthogonality and orthonormality. And in the next video, we're going to talk about the Gram-Schmidt process for finding orthogonal vectors.